For this lesson, we're going to look at polynomial inequalities, but first let's think about them graphically. Here we have a function f of x that has been graphed, and we want to know when is the function greater than 0. So based off this, what's helpful is finding first when it's equal to 0, and then we can specifically look at where the function is greater. So that would be above the x-axis in this one. Now when we're describing this interval for when it's greater, we're using our x values. This function begins to be greater than 0 after -4. So it's between -4 all the way to +1. Now at 1, we are equal to 0. And our inequality does not include when it's equal to 0. It's strictly greater. So for this one, our solution is a range of values, and it would be anything from -4 to +1, and then also 1 to +5. So what if we had changed that inequality to where it said greater than or equal to 0? This would then include these values where it is equal to 0. And so it would have a bracket at -4. But then I would not even need to break this at +1 because it would be greater all the way through +1 and ending at +5. The second graph here is wanting to look at when is the function less than or equal to 0. So again, it's helpful to find first when it's equal to 0, and then we can determine when is it less than 0. This is going to be below the x-axis. For this one, we can see it's happening from -∞ all the way up to -3. So all of these x values would have outputs below the x-axis, so we're below 0, until we get to -3. Now when we're at -3, we are equal to 0, so we're going to include -3. Then we join it together with another section that starts at -2 all the way up to when x is 0. So -2 to 0, both with brackets. But that's not the only time, because there's a third one. So we have when it's equal to 0 at x equals 3. Since this is one singular number and it's not an interval, we're just going to use the braces around the 3. A lot of people will forget this value because it says or equal to 0, and that's not a whole interval, it's just one number. If we had less than 0 and not the equal to, then we would not have that part. So what do we do when we get to number 4, when it says h of x is x squared minus 11x plus 28, and we want to determine when it's greater than 0. We don't have a graph already given to us. But based off what we know about quadratic functions, we can sketch a graph. What's helpful for this, especially for when it's greater than 0, would be to find first when it's equal to 0. Since it's a quadratic function, you can solve that whatever method works best for you. So if you want to use the quadratic formula, you can, but this also will factor pretty easily. So we're going to factor this out to x minus 7, x minus 4, which gives us two solutions for when x equals 7 and when x equals 4. Now these aren't the actual solutions to the inequality because that's for when it's equal to 0. But I can use that to help describe this inequality or this quadratic. So when x is 1, 2, 3, 4, 5, 6, 7, it's going to equal. And when x is 4, 1, 2, 3, 4, it's going to equal. Our inequality only wants when it is strictly greater than 0. Now, looking at this inequality or this quadratic function, we have a positive x squared term. Our quadratic would be pointing up. So to sketch out a graph of this, it looks something like this. which means we are greater than 0 when it's above the x-axis. This would be happening for all the values before before positive 4, and then after positive 7. So our solution to the actual inequality would be negative infinity up to 4, but not including 4 because we only have greater than 0. Union, and then 7 to infinity. So a graph can be helpful for these. It's not the only method, but it is one way to solve polynomial inequalities. Algebraically, you would first really need to know what is that function equal to 0, whether it's less than or equal to, less than, greater than or equal to. You get it equal to 0 or set to 0, and then we use the factors to help find the zeros. So this first one has 2x squared minus x is less than 15. We have a quadratic. We want to get it set to 0, so I'm going to subtract our 15, which now says this is less than 0. If I put this in factored form, I'd have 2x times x to get my 2x squared. We can try different combinations of our factors of 15. I'm going to use my 5 over here with the 2x and the 3 over here with the x because the inside would be 5x. The outside, 2 times 3, would be 6x. And together that can give me the negative 1x if I have a negative 6x and a positive 5x. So that means I'm going to use minus 3 and plus 5 there. This gives me 2 of the factors, which helps me find the zeros. So you can put this on a number line. It's going to cross the x-axis at negative 5/2 and at positive 3. Because we have a positive quadratic, a positive ax squared term, it's going to be pointing up. So if we were just sketching out a graph, we're not trying to do a full detailed graph, I know it would look something like this. So the function would be greater than 0 for this end, the ends of the function. Now this is when x is before or less than negative 5/2 and when it's after greater than 3. We describe that solution with interval notation. So our solution would be parentheses negative infinity up to negative 5/2. We're not including negative 5/2 because we're not including when it's equal to 0. Union, and then 3 to infinity. For the second question here, it's already set equal to 0. So we can go ahead and get this in factored form. Even if it wasn't something we could factor, our goal is really just to find the zeros and then use those zeros to determine when it's greater than 0. But this is something that we can go ahead and factor. We got 3x squared from 3x times x. We're looking at factors of 20. So that could be 2 and 10, 4 and 5, 20 and 1. So there's a variety of options for us. And I want them to combine to give me a 7x. All right, so let's see. 4 and 5 would work if we end up doing 3 times 4 to get 12x and 5 times x to get 5x. So a positive 12x minus 5x does give me positive 7x, which means that the two zeros are happening at 5/3 and negative 4. So whether you solved that with the quadratic formula or if you were solving that by factoring, you would get these two zeros. Graphically, this would cross here on the x-axis at negative 4 and at positive 5/3. We are looking for when it's greater than or equal to 0. So I'm going to include these 2 points because that's when it's equal to 0. The quadratic is positive, so if I was sketching out a graph, it would look something like this. This means it's greater on the ends of the function as well. Notice this time it's not just greater than, we're doing greater than or equal to. So these are the values before -4 and after 5/3. We would want to write our solution as -infinity up to -4 with a bracket, union, and then bracket 5/3 to +infinity. For number 3, it's already in factored form. So if something is in factored form, we don't really want to make it harder for ourselves by multiplying it all the way out, since the goal is to find the zeros. If we can have it in factored form, then we can easily find the zeros. So in this one, I have a 0 at +4, another 0 at -3, and another 0 at +1. Since this is a polynomial, it's a cubic polynomial, I'm going to put my zeros in order. Here's my -3, then +1, then +4. And we're strictly looking for when it's greater than 0. That means I'm not including those points because that's when it was equal to 0. This is a little bit harder since it's a polynomial and not a quadratic function. It doesn't make a parabola shape. We would have to determine our end behavior, the degrees of this function. What does that mean about multiplicities and happening at the graph or at the x-intercepts? So this graph would be a little bit harder to imagine just from the information given. It's not that it's impossible, it's just harder. So it looks something like this because all of those were multiplicity of 1. The function would be cubic, there'd be degree 3, and we'd have a positive leading coefficient. So it goes down on the left, up on the right. So it does look like this, but that might not be something we know automatically, and that's okay. What we can do is create test points to determine if we have a positive or a negative value at that point. So let's test out a value to the left of -3, something like -4. When x is -4, then our function would be -4 minus 4 times -4 plus 3 times -4 minus 1. Well, -4 minus 4 is a negative value. I'm not really worried about what the actual value is right now, but I know that it's going to be a negative. -4 plus 3 is still negative, and -4 minus 1 is negative. We end up with a negative times a negative times a negative, which is negative. All that means is that the function would be below the x-axis. It would have a negative value when x is -4. Then we're going to look at a value between -3 and 1. That could be anything between -3 and 1. So maybe -1, maybe -2, or even 0. X equals 0 is usually an easy one to plug in. So I have 0 minus 4 times 0 plus 3 times 0 minus 1. 0 minus 4 is negative, 0 plus 3 is positive, and 0 minus 1 is negative. So we end up with a negative times a positive, which is negative, but then multiplied by another negative makes this positive. So the function will be positive when x is 0. That helps me know that I'm above the x-axis during this interval between -3 and 1. I could try it out again between 1 and 4. So something like when x is 2. We have 2 minus 4, 2 plus 3, and 2 minus 1. 2 minus 4 is negative. 2 plus 3 is positive, and 2 minus 1 is positive. So when you multiply a negative times a positive, you end up with a negative. That means that third section is negative. And we pick one last section here. So something after 4, like when x is 5. If I plug in 5, we have 5 minus 4 is a positive, times 5 plus 3, which is a positive, and 5 minus 1 is a positive. A positive times a positive times a positive is positive. So if the goal was to figure out when the function is above 0, that was when it was positive. This happens graphically between -3 and 1, but even algebraically we can prove that it was happening between -3 and 1. Graphically, it also happened beyond 4, so when x was greater than 4. Another algebraic method helped us see that it was also positive for anything bigger than 4. So our solution, which I don't have room to write over here, but I'll write it underneath. Our solution would be the values between -3 and +1, union 4 to infinity. This method using these test points is called the sign chart analysis, where we're really only focused on what is the sign of the function during that interval. So if we look at number 4, it's already in factored form for us. I can find when it's equal to 0, and that would be at +3 and at -5. If I did a number line with -5 and +3, our goal is to figure out when it's greater than 0. I usually write this off to the side here just to give myself a little reminder of what I'm looking for. Since I'm looking for when it's greater than 0, I know I'm not including these values -5 and +3. This polynomial might be harder to graph, or maybe it just takes a little bit longer to sketch out a graph. So using a sign chart analysis can be helpful. So let's do our sign chart. By picking values to the left of -5, this could be something like -6. If I do -6 minus 3 squared times -6 plus 5, any number squared is going to come out positive, so I don't really care what the inside is. It is squared, it's positive. -6 plus 5 is negative. So this ends up being negative for any value to the left of -5. Then we would have a number between -5 and 3. 0 is in that interval, but so is +1, so is -1, -2. There's so many that you could choose from, but I'm going to use when x is 0. So 0 minus 3 squared times 0 plus 5. Well, 0 minus 3 squared is positive because it's squared, and 0 plus 5 is still positive. So we get a positive times a positive, which is positive. That means any number in between -5 and +3 will have a positive output. And we choose a number to the right of 3. So I'm just going to do when x is 4. That gives me 4 minus 3 squared and 4 plus 5. That is a positive times a positive, which is still positive. So if the goal is to determine when the function is above 0, when it's greater than 0, that would be these values where the function was positive. So we are not including -5 or 3, but we do get this resulting interval. So our solution would be -5 to 3, both with parentheses, union 3 to infinity. So So what if this had been or equal to? Let's just think off to the side here for a second. What if it had said when greater than or equal to 0? In that case, I would get to include those values, -5 and +3. So I'd have like a closed dot here at -5 and a closed dot at +3. It would still be negative before -5, positive between -5 and 3, and positive after 3. Which means I'm including that all the way to infinity. So from -5 up to infinity, I wouldn't need to break it at 3. Our solution would just be -5 to infinity. And lastly, we have number 5 here. So 6x cubed minus 36x is less than -5x squared plus 30. With this, it's not already in factored form. But we have this cubic inequality, so we first need to get it set equal to 0. And I'm going to do that by moving everything to the left. So that would mean moving my 5x squared term over to the left. We already have minus 36x on the left, and then also moving my 30 over to the left, so minus 30 is now less than 0. This is one that we have to factor. If that can't factor, we're kind of screwed. So we do need this to factor. Since it's 4 different terms, I'm going to try factoring by grouping. The first group, 6x cubed plus 5x squared, has a GCF of x squared, and it leaves me with x squared times 6x plus 5. Then we look at what's going on with the other part, the other pair. Negative 36x minus 30 has a GCF of -6, which leaves us with 6x plus 5. So we can factor this by grouping into 6x plus 5 times x squared minus 6 is less than 0. X squared minus 6 cannot factor further, so this is in completely factored form. And just for good measure of showing my work, I'm going to set these equal to 0 so you can see what the 3 different solutions to that equals 0 would be. So we'd subtract our 5 and then divide by 6 to get -5/6. But then we would add our 6 over, square root, so positive or negative square root of 6. These don't have to be pretty answers. All right, we find them on our real number line, but I need to determine where is the square root of negatives, or the square root of 6. So if we find the decimal equivalent of the square root of 6, it's roughly 2.4, and so negative square root of 6 is going to be -2.4. Which helps us figure out where that is in relation to -5/6. So negative square root of 6, and then -5/6, and then positive square root of 6. We're strictly looking for when it's less than 0, which means I'm not including these values where it was equal to 0. I don't know exactly what the graph looks like. I could think about the multiplicities and things. These all have multiplicity of 1. We could look at the degree, all that stuff. But really our sign chart analysis really helps us as we get to more advanced inequalities. So you pick a number to the left of negative square root of 6. Well, negative square root of 6 was -2.4, which means I could pick something like -3. But you can go more extreme. You could plug in -100 and know that you're to the left. It doesn't matter as long as it's in this furthest interval. You can plug this into factored form or into the original inequality. I like using factored form, so 6 times negative 3 plus 5, and then negative 3 squared minus 6. We're going to get negative 18 plus 5 is still negative. Something squared, so negative 3 squared, that's 9. 9 minus 6 is still positive. So we have a negative times a positive, which is negative. And you don't really have to rely on your brain to do that. You can plug this into your calculator. You will need to look to see, like, when you're putting negative 3 squared in, it still goes in parentheses, but I get negative 39. That is a negative value. And then we test out something between negative square root of 6 and negative 5/6. So if that's roughly negative 2.4, that means I could try something like negative 1. 6 times negative 1 plus 5, and negative 1 squared minus 6. Negative 1 times 6 is going to be negative 6, but negative 6 plus 5 is still negative. Negative 1 squared is positive 1, and positive 1 minus 6 is still negative. So I get a positive result in between the square root of negative square root of 6 and negative 5/6. We try something between negative 5/6 and 6. So x equals 0, that might be the easiest one. 6 times 0 plus 5, and 0 squared minus 6 gives you a positive number times a negative number, so that is negative. And lastly, we choose something to the right of the square root of 6. So this is roughly 2.4. Something to the right of it could be positive 3. All right, so if I plug in positive 3, I get 18 plus 5, that's positive. 9 minus 6, that's still positive. So a positive times a positive is positive. We are looking for, when is this function less than 0? That was here to the left of the square root of 6, negative square root of 6, in between negative 5/3, negative 5/6, and the square root of 6. So we get some uglier numbers, but our solution process was still the same. Our solution would be negative infinity up to negative square root of 6, then union, negative 5/6 up to positive square roots of 6. And we can use these inequality methods for different applications.